Good evening. Hi everyone, welcome to Langlab, welcome to Pop-Up University. My name is Stephanie, I'm the owner here at Langlab. We are an arts and business incubator. We have a number of things that are going on almost every day of the week here. But one of the things that has been the most longevity is Pop-Up University. It's a collaboration between Langlab and Indiana University South Bend, and the idea is to bring the best and brightest from the IU South Bend campus here into the community so that we may discuss, hear about them, hear what they're working on, and be able to join together as a community outside of the university system. So I would like to say just a couple of things. First of all, if this is your first time here, I don't know if there are many of you, but if it is, we have a single bathroom right on the other side of those doors. We have a larger set of bathrooms right through there. Our bar is open until 10. It is actually open from 6 p.m. to 10 p.m. Monday through Saturday. We also have the cafe open, which is called Everett's Treatery. They are open from 5 p.m. to 9 p.m. Wednesday through Saturday. And our newest endeavor is High Street Station, which is our arts consignment shop. We have hundreds of items on sale that are made completely locally by artists here. So everything from actual large paintings to mugs to keychains to patches, all kinds of stuff. That is also open from 4 p.m. to 9 p.m. Wednesday through Saturday. However, we will be kicking off our holiday market the Friday after Thanksgiving, and we are going to have an extravaganza on Small Business Saturday. We're going to be doing bar specials. We're going to be doing brunch with Everett's. We're going to have a professional Mr. and Mrs. Claus here for photo opportunities. There will be a flea market, and we will be kicking off our holiday market, which we have called the Yuletide Bazaar, which will then be open from the entirety, from the Friday after Thanksgiving all the way to New Year's. So we invite you to come out and see what the best of South Bend art scene has to offer. And with that, I'm going to turn it over to Elizabeth to announce our speakers today. Thank you.
All right.
Thank you so much, Stephanie, and thank you for allowing us to use this wonderful community space. I'm Elizabeth Bendian, Director of Community Engagement at IU South Bend, and tonight we have the privilege of hearing from two professors who are actually IU South Bend graduates.
Yeah.
Yes,
Right.
exactly. Dr. Maggie Fink teaches biology at IU South Bend. She earned her PhD in microbiology from the University of Notre Dame, where she focused on bacterial genetics and science communication. She also holds a BS in biochemistry from IU South Bend and a BA in theology. Fink's work bridges science and storytelling, and she is passionate about making complex ideas accessible, which I'm sure we all appreciate. She hosts Rust Belt Science with Shahir Rizk, our other speaker this evening, and she co-authored with Shahir The Color of North, which explores how proteins shape life and the future of biotechnology. Our second featured speaker this evening is Dr. Shahir Rizk. He is an associate professor of chemistry and biochemistry at Indiana University South Bend. He holds an adjunct appointment with the IU School of Medicine. A protein engineer by training, he earned his PhD in biochemistry from Duke University and his BS, again from IU South Bend. His research explores protein structure and function, including engineering enzymes to combat disease and designing biosensors for environmental monitoring. So practical civic uses, which I love. Rizk co-hosts the podcast with Maggie Fink. And as I already mentioned, they also are co-authors of a book, and you see the cover photo there on your screen. And What they're going to talk to us about today is the art of discovery, merging science and creativity. And I know we have some folks with science backgrounds and some folks with art backgrounds in the audience this evening. So the question is, how do scientific breakthroughs emerge from creative thinking? And so they will explore this evening the dynamic interplay between scientific inquiry and artistic imagination, drawing from their research, personal journeys, and popular Rust Belt science podcast. They will help to illuminate how curiosity, creativity, and collaboration fuel discovery in both the lab and the broader world. From protein engineering to poetry, from Rust Belt resilience to northern landscapes, they will invite us to reimagine science not as a rigid and perhaps for some of us seemingly inaccessible discipline, but instead as a vibrant, creative process that shapes how we understand and how we engage with the world around us. So please welcome Dr. Shahir Rizk and Dr. Maggie Fink.
We sound so much cooler than we really are. Thank you for this introduction. I want to start with a reading from our book. This is Taking Form. Linus Pauling was restless. The 47-year-old scientist who was often sickly and too weak to work had fallen ill with a cold and was supposed to stay in bed for 3 days. It was the year 1948, and Pauling, bored with reading detective novels, turned his attention to a question that had been on his mind for months. What do proteins look like? At the time, very little was known about protein structure. Pauling, a chemistry professor at the California Institute of Technology who was spending the year as a visiting professor at Oxford University, was an accomplished chemist. But even for him, protein structure remained elusive. Many scientists had worked with complicated machinery and devised complex formulas to try to predict what shapes proteins took on, yet very little was clear. Pauling took out a piece of paper and scribbled down a few chemical structures, sketching out what was known about proteins. He drew carbons and oxygens and connected them to nitrogens and hydrogens in the way he knew that amino acids, the building blocks of proteins, were arranged. He worked until he had a repeating pattern of chemicals. The letters formed a long line across the page, which he cut out into one long strip. Then he took the strip of paper and twisted it around itself, carefully lining up the atoms that attracted each other, and found that the strip twisted into a spiral. That February morning in Oxford, Pauling had stumbled upon one of the most fundamental shapes found in all living things. He had discovered the alpha helix, a shape that would later become synonymous with the language of proteins and the building blocks of life itself.
Thank you guys so much. Oh yeah, just stay by the mic. Thank you guys so much for coming. I'm a little nervous talking in front of some of my professors that I had when I was at IU South Bend. So hopefully I get an okay grade. So I'm so grateful to be here and talk about why I love science and why I'm passionate about, and Shahir and I both are passionate about bringing art into science. So you heard Shahir talk about Linus Pauling briefly from our book. We'll talk about him in a few minutes again. You might recognize this alpha helix shape from DNA, but it also exists in other biomolecules, so we'll talk about that. As Elizabeth said, I'm actually a microbiologist by training. I started off with biochemistry. Now I'm a full-blown microbiologist. So I want to start off by talking about some of my favorite microbiologists and the cool discoveries they made and how they use their creativity and curiosity to come up with these ideas. So about 400 years ago, there was a man named Antony van Leeuwenhoek. He was a Dutch merchant, so not technically a scientist. He dabbled in the sciences, self-taught scientist, they would describe him as. And he's actually known as the father of microbiology, and he wasn't even really a microbiologist. So Leeuwenhoek actually invented one of the first microscopes, which it's a little bit difficult to see in this image. I'm going to walk away from the mic and point to it and use my teacher voice. You can see here, Leeuwenhoek is holding up a very small thing close to his eye. Not that traditional microscope that you might imagine that has this big eyepiece and we make adjustments. He's actually holding up a very small piece of metal with a screw and a lens that he made himself. And he kept it a secret from everybody else. Nobody knew how he made these lenses. And he looked at anything he could find under the microscope. So down there in the bottom right, you can see that is part of a birch tree that he looked at under the microscope, and he drew all of these images himself as well. So he was a very talented artist. And most scientists back then, they didn't have cameras to capture things they saw, so they had to draw them. We've seen images of Darwin's drawings as well. So this was a very common practice for scientists to write down and draw the things that they observed. You can see there figure 2, that is actually some sperm that Leeuwenhoek looked at under the microscope as well. And then he also characterized a lot of insects like fleas and flies that he drew images of. My personal favorite, because I'm a microbiologist, is one day Leeuwenhoek decided to scrape some of that gunk off of his teeth that we all have in the mornings. Those are biofilms. That's bacteria that has made a home in your mouth, and we should keep it there. It's good for us to have some bacteria in our mouth. And he scraped that off, and he looked at it under the microscope, and he described what he saw as animalcules very prettily moving along. And he was one of the first people to describe seeing bacteria. He called them animalcules. So this man, who was not a scientist by any formal training, he actually sold cloth, was one of the first people to describe what we now know is this vast microscopic world that's on our skin, in our stomachs, on the ground, on the dog that was in here. All of these things have bacteria everywhere. And so that's why Leeuwenhoek is one of my favorite scientists, and really exemplifies the practice of science historically as one that's being fueled by creativity, artistry, and mostly curiosity, looking at something that we would otherwise want to get rid of very quickly, our morning breath discovered bacteria. Another microbiologist, this many hundreds of years later, is Sir Alexander Fleming. And you probably know him most from penicillin, right? How many of you have taken penicillin or another antibiotic in your life? Probably everybody, or else we'd all be dead, right? So Alexander Fleming was notorious for being a very untidy scientist. His lab was often filled with dirty dishes. He didn't clean up after himself. He was always tinkering and playing around with different bacteria. He had many significant scientific discoveries, but the one that really catapulted him into fame and changed the world was the discovery of penicillin. So, as a good scientist does, Fleming was on vacation one week. So he left all of his dirty dishes, which, as a good scientist does, left them there to be somebody else's problem or next week post-vacation problem. When he came back, he had started growing some bacteria on one of those petri dishes you might be familiar with, a bacteria called Staphylococcus aureus, or Staph aureus. You might recognize this from something like a staph infection or MRSA. So that's an antibiotic-resistant form of staph. So he was growing some staph just to see what would happen with it. And he came back a little bit later, several days later, and there was some bacteria growing on the plate. And next to it was growing a fungus. And he noticed that wherever the fungus was, around that area, there was no staph growing. He said, "That's funny." That is historically accurate. That was his response. "That's funny." And rather than just toss it into the trash, like I probably would have done when my plate is contaminated with mold, he was curious about why there was no bacteria growing. And a little bit of research later, he discovered that that mold was making something called penicillin, which is an antibiotic, and it was actually killing staph. So if you'll notice the year I have here, it says 1928, so this is when he first discovered this. World War II happened a little less than 20 years later, and it wasn't until right before World War I that he was actually able to get penicillin to be made and synthesized and get it purified in a lab so we could use it as an antibiotic. And during that whole time, a lot of people thought that this discovery was insignificant, that it didn't matter, and he was stupid for pursuing this. Then come World War II, and having this antibiotic, and what we would soon discover many other ones, changed the war. We were able to save, not we, I wasn't there, but microbiologists, this discovery was able to save countless lives through these treatments of antibiotics. And this was driven, again, not just by dirty dishes and untidiness, but a genuine curiosity about what was happening right in front of him, and to not assume that a mistake was made, but to be curious and observant about the world around him. And he won the Nobel Prize for this, I believe. So this is Linus Pauling, another one of my favorite scientists, and I know one of Shahir's favorite scientists as well. So we're no longer in the world of bacteria, unfortunately, but my second love, proteins. So Linus Pauling is an absolutely, unbelievably wonderful, brilliant chemist. And he discovered or came up with how we could solve the structure of protein. So we all are probably familiar with what DNA is, right? We have seen that famous helical structure. We've heard about the controversial figures of Watson and Crick, and that the DNA is the genetic information for life. It codes for everything that makes us who we are as individuals. But all that DNA is instructions. The cool stuff is actually what these instructions are for, and that is for making proteins. And so maybe you should read our book because we talk more about that. But nobody knew what proteins looked like, right? We knew that they were important for doing all of the things inside of our bodies. Yes, our DNA and subsequently the proteins can dictate what our eye color is and all those cool, fun traits that we learned about in high school biology. But proteins also help us digest our food. They help us sense the world around us. But we didn't know what they looked like or what shape they took. So Linus Pauling, like Shahir read, was sick in bed and was just tinkering around with some ideas. How can we figure out what proteins actually look like? And so through modeling some chemistry and thinking about hydrogens and bonds and all that stuff that our chemistry students are trying to memorize right now, he figured out that similar to DNA, proteins can adopt a helical shape, which you can see represented kind of here with Linus Pauling. It looks a little bit different than we would represent it now. But even in that image in the top middle there, these really cool spiral helical shapes. That's just one of the ways that proteins can form three-dimensional structures. And him just imagining what could be happening at that beyond microscopic level led him to solve this huge problem that now has revolutionized protein chemistry. And he won a Nobel Prize for this, and he is also the winner of the Nobel Peace Prize. So this man is unbelievably talented. He's dead now. He was unbelievably talented and just a very good human being. And that was inspired by the world around him. One more protein scientist that I want to talk about. This is Jane Richardson, the mother of the ribbon diagram. Unlike these other people, Jane is not actually a scientist. She was trained in the humanities. She was an English major, but she worked in her husband's lab, who was a protein scientist. At this, I don't remember what year this was. Do you remember what year this was that she did this?
50s, 60s, maybe.
Okay, 50s, 60s. Again, I was not alive then. So again, we knew what proteins looked like. We knew that they adopted these three-dimensional structures. But as you can see here on this far left, when we try to write out all the parts of the protein, it's very complicated. There's carbons, there's hydrogens, there's nitrogens, and it gets really busy, and it can be hard to actually visualize what's going on, right? So Jane had this idea that what if we represent proteins like ribbons, right? You've seen those ribbon dancers, and you can see this M.C. Escher image here as well. She was inspired by art and the way that these ribbons could depict three-dimensional structures. So what she proposed that we do is we strip away all the chemistry happening at that, again, beyond microscopic level, and just represent it as a shape, as this ribbon. So here we can see the alpha helical structure of proteins. There's other structures that proteins can take too, and they can all be represented in this really simple way, all because Jane used some imagination. And I know Shahir might have a little story about her. He knew her when he was in graduate school, and we had the opportunity to talk with her a couple of years ago as well. So she is still alive and well, unlike all these other scientists. But her contribution to the field of biochemistry and protein structure as a not trained scientist really showed the importance of marrying these two worlds of the sciences and the arts and the humanities.
Jane's super cool.
Yeah.
Imagination is central to science. It's really, really important. You may have heard of Gregor Mendel. He is the father of modern genetics. He came up with the concept of a gene, all based on breeding these pea plants and just looking at color and shape and size and so on. And mind you, this was before we knew anything about DNA or any of the chemical structures that we know now. He came up with that concept just based on just the work that he did with peas in his garden in a monastery. He was a monk. And this is another story that I really enjoy, and it's the story of the cone snail. There are scientists who are studying the poison or the venom in the cone snail. This is a very peculiar creature that has a stinger. It's a harpoon that it stabs into whatever creature it wants to eat, and then it swallows them whole. And essentially, the scientists were just really interested in this cool organism. This is why we really need to fund far-out research, because what came out of it is some amazing therapeutics. And it all took really a crazy experiment that was done by a bunch of undergraduates to analyze the venom of this creature. And they found that it had a bunch of different toxins that can kill you in many different ways. Each one can kill you in a strange, weird way. Not you, but mice. And, well, but also you, but they confirmed it in mice. And in fact, they found that many of these protein poisons that are in the venom, something like 800 different proteins in a single injection of venom, each one can have a different way of activity, of working with the the nervous system of the victim. And now we're using some of these to develop things like artificial insulin for patients, but also ways for pain relief, for severe pain. And you probably didn't expect us to talk about aliens today, but it takes a lot of imagination to think about aliens. And maybe in the comic books that you read, aliens are these green creatures with little antennas. But as scientists imagine what aliens could be really like, we're thinking of microorganisms, things that are very much like the bacteria and the microscopic things that live here on Earth. Those scientists are called astrobiologists. They do exist. And they are studying what life would be like on different planets. The planets out there have sunlight that's different from the sunlight that we have with our sun. And the idea here, at least the consensus now, is that most likely they're going to be purple because of the type of light that they get, not green like the plants that we have here on Earth. And so it takes a lot of imagination. And then, of course, in my field of bioengineering or protein engineering, these beautiful structures here, the question that I'm always trying to answer or trying to ask is, can we make new structures, can we make new functions so that we can introduce new scaffolds and new ways of making proteins with new function that nature has never seen before? Can we use that for detecting pollutants? Can we use that for curing diseases and for things like environmental problems like carbon capture and so on? You can't really do any of that without having imagination. Unfortunately, that's not something that's really viewed so much by people outside of the scientific realm, that somehow science is based on imagination, because a lot of times some of our interactions come from what we want to call the dogmatic scientist. These are quotes by two very well-respected scientists, by the way, two very well-accomplished scientists here that I just wanted to share with you today. Anybody heard of Richard Dawkins? I know all the biology people here have heard of Richard Dawkins. Amazing scientist, really, an evolutionary biologist. And this is one of his quotes: "Religion is capable of driving people to such dangerous folly that faith seems to me to qualify as a kind of mental illness." And just by saying that, now he has alienated so many people in the world who hold any kind of religious belief. And it's one thing to disagree with people on what they believe in. It's another thing to call them mentally ill. And we may have heard of Neil deGrasse Tyson. Everybody heard of him? Great guy, amazing science communicator, but sometimes it's kind of my way or the highway. And I guess that's one way to do it. The good thing about science is that it's true whether or not you believe in it. So falling down the stairs, I don't have to believe in gravity. I will still fall down the stairs. He's right about that. But unfortunately, if we as scientists are talking to people by alienating them, then we end up with what happened, and we've all seen it with the COVID pandemic and the resistance that so many people had to things like vaccines, or even just sound medical advice like wear a mask or just don't cough into people's faces. That's probably good advice. And what that did is it really caused a large degree of spread of misinformation. There's a lot of misinformation that was spread. And I mentioned COVID here because it really brought up to the surface what we as scientists and science communicators knew was happening for many, many, many years. Anti-vaxxers have been around forever. In fact, since vaccines were developed, a couple hundred years ago. And it's just really come up to the surface then. So the spread of information is a real thing, and science tells us that misinformation spreads about 6 times faster than accurate information. And as a scientist, I'm standing here today to take some responsibility for this, to say that we have done really a poor job of really interacting with our communities and interacting with them as human beings and connecting with them. And what happens with misinformation is that it often leads to conspiracy theories. Things like the earth is flat, right? Or yes, or the moon landing was fake, or COVID was made in a lab. And, it's really conspiracy theories, what are conspiracy theories? These are really things that people believe about some sort of group of people that have conspired to do something to us that is out of our control, and it's usually there to explain some sort of big global phenomenon. And of course, something like a global pandemic is going to be, a breeding ground for these kinds of misinformation. Something like the Kennedy assassination or Princess Diana, right? Yes, that's a long story there. Princess Diana, so on. All of those lead to all sorts of conspiracies. But why do we fall for them? And when I say why do we fall for them, I mean that intentionally, because we all fall for conspiracy theory. Nobody's immune to it. Some people are more prone to it. But all of us, every single one of us, research tells us, believes in some sort of conspiracy theory. I'm happy to share mine with you later on if you want to. But, why do we... Yeah, happy. It's a public talk. But why do we like them so much? Why do we, again, I'm using this intentionally, why do we fall for conspiracy theories? Anybody have a good idea? Why? Why do we like them so much?
A lot of times they're great stories.
It's a great story. That's exactly it. It's a great story because I'd much rather believe that the people who are charged are reptilian aliens from, shapeshifters. You heard of that one? Right? Something like 20 million Americans believe in that, more than the population of Sweden. People live, yeah, it's insane. Sorry, I don't mean to call anybody insane. I just did it. The climate is insane. How about that? But basically, it's far more fun to believe that the world is ruled by shapeshifter aliens, reptilian shapeshifters, rather than just people who don't really care about you and me, and they're just power hungry. That's a far more boring story than the reptilian aliens. And so, what can we as scientists do about it, and collectively, what can the rest of us do about it? And I think this is something that hopefully we'll be able to talk about a little bit today. We have to be able to connect with people on a human level. We have to be able to do that. And I want to talk a little bit about something that caught my attention from this book by Charles Duhigg. It's called Super Communicators. He's not necessarily talking about science communication, he's talking about communication in general. And he describes the 3 different conversations. This is just the 3 different types of conversations. The first one is, what is this about? And it's really about facts. So, what time are you coming home? Okay, 7, all right. Are you going to pick up dinner? Okay, great, fine. And then how do we feel, right? These are conversations about our feelings. And then finally, who do we belong to? Who are we? What is our group? And what are our values? And these are the 3 different types of conversations. And so I can say, I have to go to work tomorrow at 8 o'clock. Well, that most likely is going to be this kind of what is this about conversation. But I can also say, I have to be at work tomorrow at 8. Is this also this type of conversation here? Not really. This is really more of a conversation about emotions, even though it is conveying information. Really, it's a conversation about how I feel about work. And what happens is that for scientists, when we are talking to somebody who, say, is reluctant to take a vaccine, for example, they come and ask us, and they tell us, why should I take this vaccine? And what do? We state a bunch of facts. We just tell them, here's all the facts, here's all the data plots, here's all the data, here's all the statistics, here's what's going to happen to you if you take it, here's what's going to happen if you don't take it, right? And then what do they actually do? They're talking about how afraid they are to put something in their bodies. They're talking about how afraid they are to put something into their children's bodies. And that's something that's very legitimate. It is a feeling that we all have. We all want to protect ourselves, and we all want to protect our children. And what do we do as scientists? We fail to recognize that this is the type of conversation that's being had, and we continue on this, fact mission. And all we're doing is that we're just presenting facts, and we're saying, why are you not understanding what I'm saying? Well, because it really has nothing to do with whether it's about facts. We don't recognize the feelings. And it could be, the conversation can go into the third type of conversation of, who are we? Am I the type of person who is going to put this lawn sign on my lawn, or that lawn sign on my lawn? Am I the kind of person who would put a lawn sign on my lawn in the first place, right? Because it's really about belonging. Who am I? Yet again, as scientists, we fail to recognize this most of the time. And so we need to do something about that, and we need to do it better.
So I want to talk a little bit about how science and the arts go together. Hopefully I convinced you from all those super cool scientists that art and creativity go hand in hand with scientific discovery. And I think as scientists, we've done a very poor job at showing that maybe science is a little bit more loosey-goosey and more playful than somebody like Neil deGrasse Tyson might present to the world, right? He's great. He shares awesome information. He also has the privilege of talking about things that are a little bit less controversial, like outer space. Everybody loves outer space, right? But when you're working with things like vaccines, working in the biomedical sciences, it can be a bit tricky. And so I want to talk about how Shahir and I view using art in the sciences to address some of the misinformation and the distrust that people have of scientists, and how science actually works, and using art to do that. Right? How can we bridge this gap using art and stories? And I was so happy somebody brought up the fact that conspiracy theorists have better stories than scientists have, right? We tell very boring stories. And when in fact, if you actually talk to a scientist kind of over a beer, we'll talk for a really long time about really cool stuff. So we want to do a better job at that, and specifically through art and storytelling. And when I'm talking to other scientists, trying to help them communicate their science better, the first thing I say to them is, what you lose in accuracy, you gain in power, right? I could have sat up here and talked to you all about the technicalities of Leeuwenhoek's microscopes, about hydrogen bonding in alpha helical structures of proteins, but that's not going to do anybody here any good, right? I'm glossing over a lot of details that other scientists might criticize me for because it's not technically accurate, but you got the message, hopefully, right? Hopefully I left you with something a little bit more powerful and impactful. And using art to do that as a scientist, and even as an academic in general, I know there's a lot of academics here who are not scientists who face similar problems to scientists as well. There's a general distrust in academia. So how can we use the arts to do that? And this first bigger image here is a stunning piece of art by one of my favorite artists. She makes these beautiful life-size textile sculptures to represent the human microbiome. They're very stunning, right? And I could sit up here and give you a bunch of graphs about all the information about the human microbiome, which would be cool, or showing you a piece of artwork to represent how complex, how diverse, how magical the fact that we are literally swarming with bacteria right now, and they're influencing how we think, what we like to eat, how we sleep, what diseases we might get, all of these things, right? Which you could come take a class that I teach at IUSB about that. But I can also show you a piece of artwork to convey that message. Down here at the bottom, probably everyone here from the Rust Belt has been to Chicago and seen the bean. But you might not know that the bean was actually heavily influenced and inspired by science. The bean was made by an artist, and I'm totally blanking on the name right now, and they were inspired by liquid mercury, right? I remember my grandparents had a mercury thermometer when I was young. Hopefully that doesn't exist anymore. But it's really stunning and really beautiful the way that it moves. And the artist was also inspired by the way that it reflected the light in the sky. So yes, this is a very famous Midwestern landmark that everyone takes pictures with, but it tells us something about science, right? Salvador Dali down at the bottom was really inspired by physics when he was making his art pieces. That one at the top, it's a little difficult to see here, but that's actually a microscopy image. So that is a piece of data that a scientist collected. And you can see these bright, vibrant colors in this plant stem and these leaves. Right? It's beautiful. We get to take these really stunning, beautiful, artful images that convey information while also sparking that curiosity. And that one right there in the middle is this beautiful life-size structure to talk about climate change and how it's impacting coral reefs. Again, I could tell you all, well, I couldn't, I'm not a climate scientist, but I could show you a bunch of data about climate change, or I could have you engage in some art and evoke an emotion, evoke a feeling, and find a way to connect to your own identity through art. That's why art is so powerful to do this. And like I said earlier, scientists traditionally have done a lot of art in their data collection and their observations. And in fact, most Nobel Prize winners and the scientists are proficient in some other form of art. I wanted to share a couple of things that Shahir and I have done over the years as well, specifically in this case talking about protein structure. We made this piece several years ago when we were in North Carolina. This represents a protein structure called amyloid beta, and this is responsible for Alzheimer's disease. My grandfather passed away from Alzheimer's a few years ago, and essentially what happens is we have this protein in our brain, and it functions. We don't understand fully the function of it. We know it exists, and it has this very specific structure. But when this disease occurs, that protein begins to unfold and unravel and take on a very different shape, which you can maybe kind of see represented by the wires at either end of it. And that causes a chain reaction in the brain, and it causes other healthy proteins around it to also begin to unravel and to spiral. And they form these large aggregates, leading to the devastating disease of Alzheimer's. Again, I could sit up here and talk to you about the science of amyloid beta and how it affects the protein structure and all the genetics behind it and all da-da-da-da. It's really boring. I could show you a piece of artwork. The pictures here are actually a stack of photos that Shahir and I found at a random thrift shop when we were in North Carolina. I don't know who they belong to. I don't know who these people are. They are lost memories, and so we decided to create this structure, right? And in addition to the art component of this, I can tell you about my grandfather, who was the coolest Indiana Hoosier you've ever met. He owned a car mechanic shop down in Anderson, Indiana, and then he didn't remember who any of us were anymore. And that's really sad, and that's really devastating, and it's something that probably somebody in this room has experienced with a loved one as well, going through dementia or Alzheimer's. So there's a way that we can talk about science, and there's a way we can talk about our academic research that actually connects to people. And yes, maybe I misspoke and didn't technically say all the correct things about amyloid beta, but maybe it brings comfort and curiosity to people who can relate to this experience. Another thing I did, a little bit more fun than Alzheimer's disease, is making some comics. And this was actually a huge start of Shahir and I's work in science and the arts, and it's because of a professor at IUSB, Dr. Kelsey Urbick. I took a random class when I was a student, writing creative nonfiction. So anybody who knows Kelsey knows she's an incredible writer as well as an incredible artist. And so I took this class, and it turns out we had to draw pictures and make graphic nonfiction pieces. So I made this piece just on a whim one night when I needed to turn in an assignment. I was studying proteins at the time, so I decided to draw a bunch of protein structures and give them essentially characteristics and personality. So we had to talk about relationships through a comic. So here in the top left is the protein called hemoglobin. Right? Maybe you guys have heard of this one before. This is important for transporting oxygen in the blood. And so I drew the structure of it, and I wrote sometimes a group of people work together cooperatively. So the way that hemoglobin takes its shape and carries the oxygen, we call that cooperativity. So I gave it a little bit of a personality. And this one down here in the bottom is an antibody, again, something you may be familiar with or have heard of. So an antibody is like a friend. The good ones identify your bullshit, right? So an antibody is in your bloodstream and it tries to find things that are foreign invaders and say, this doesn't belong here. And it triggers this cascade in our immune system. That's how we can respond to infections and things that might cause allergies, right? Those are our antibodies. Let's see what's another one in here. That one right in the middle, that is called green fluorescent protein, or GFP. This is a protein that glows. It glows this really beautiful bright green when it's exposed to UV light. So we as scientists use this all of the time for all kinds of assays and experiments, right? That microscopy image I showed you earlier probably had some GFP in it, right? So cells can make this protein and we can observe them in these really beautiful colors. And it was actually first identified and characterized from a jellyfish in the ocean. And somebody won the Nobel Prize for this one as well, because they're like, why is this jellyfish glowing green, right? So again, curiosity, and then it's represented here. So this friend who is like GFP, all of them make life colorful, right? So this silly little comic really started to show me that I can use art to talk about science, right? None of these are technically accurate. No research journal will publish these images, but I got to show my non-scientist classmates what was happening in Northside Hall in IUSB. So many thanks to Dr. Kelsey Ervik for really inspiring us to continue this work with drawing protein structures. So scientists really need to find a way to connect through personal values that they share with the community. And I'm going to hand it over to Shahir to kind of wrap up, talking a little bit about other ways that we as scientists and academics can do this.
Another art form here that's also near and dear to our heart is writing about science. And maybe some of you have recognized these books or have seen them or have read them. How many of you have heard of Mary Oliver? Mary Oliver, amazing poet, and she really talks about nature. It's really a beautiful way to describe nature. All of these I consider are science books in one way because they do talk about nature, and they range from the poetic, like Mary Oliver and Wendell Berry, to the narrative nonfiction. This is one of our favorite books, Braiding Sweetgrass by Robin Wall Kimmerer, an indigenous ecologist and botanist who talks about indigenous practices and how they tie to modern ecological approaches. Very narrative, very personal. And this is also a really great book about whales. And then they range all the way to the reporting type narrative, where they pick a topic and they write reports about it. This is a really great, gory, detailed account of what surgery was like back in the Dark Age. Well, not in the Dark Ages, but over the last few hundred years. Just a great book. And Ed Young as well, I believe he's a Pulitzer Prize winning author. So there's a huge range here, and again, the common thread here is that all of them are telling a story, whether in poetry or narrative nonfiction or reporting on a story or talking about history. And so going back to the three conversations, the best way to really engage with someone is to tell a story. This is something that we've done for years and years and years and years, for eons. We sat around fires and told stories, and today we still do that. We maybe do it through music or art. We sit around a fire, even if it's just online. We sit around a Zoom and we tell stories. Hopefully we still tell stories, because that's how we can connect with people on an emotional level, and we can connect with them through values. If I read the book to my kids, The Boy Who Cried Wolf, it's a really impactful book, not because it's about the biology of wolves, but it's because it's a story about the consequences of lying. It's far better to read them that story than to tell them, don't lie, lying is bad, don't lie, lying is bad. It's much better to actually get that story. And so we are all born scientists and artists. Ever since we're toddlers, we pick up stuff, we put it in our mouth, and if it tastes bad, what do? We spit it out. That we just did an experiment. This is the scientific method. Ooh, hypothesis. Ooh, testing. Conclusion, bad. We just did an experiment. We are all born scientists and we are all born artists. But most of all, we are storytellers. And unfortunately, many of us in the sciences, for good reasons, again, I'm not dumping on this, for good reasons, we have put away our storytelling because we communicate through plots and data points and graphs and jargon that has ultimately ended up alienating us from others in the community. And what we need to do is really untrain ourselves as scientists to be able to engage with people, especially those that we might disagree with, or people who might think that we are just out there or we're trying to indoctrinate them. So our mission is really to bring back that childlike wonder to both science and art, and this is really about fostering fascination to change the conversation instead of saying, take this pill or you're gonna die, and if you don't do it, you're stupid, right? Because that's sometimes what we sound like. It's really about engaging with people to change that conversation and instead fostering fascination. We want to do that through art and through storytelling. I want to just end really quickly, but one last reading from the book, if you will allow me, about our favorite molecules, proteins. According to the Bible, the first miracle Jesus performed was turning water into wine at a wedding celebration. Later, he made a paste from dirt and spread it over the eyes of a man born blind. When the dirt was washed away, the blind man could see. The miracles became more and more elaborate, healing the sick and lame, calming storms, and raising the dead man from his tomb. These acts of supernatural power may seem far-fetched, defying our understanding of life, but every day, small miracles happen all around us. Within our liver cells, enzymes turn toxins into harmless molecules. Defensins protect us from infections, and light receptors illuminate the world around us. And it all happens without us having to think about it. Inside every organism, proteins live in a world all their own, dynamic, responsive, and alive. They are more than simply tiny molecular machines. In many ways, they are microscopic miracle workers. While our DNA may dictate who we are genetically, it is merely the instructional manual for how to put all the pieces together. Proteins with their three-dimensional shapes, movable parts, and complex chemistry are what make us who we are. They remember the places we have been and where home is. They store the memory of citrus on our tongues during a cold winter long ago. They form the bond between a mother and child. They protect us from threats of all kinds. They connect us to the web of life on this planet, enabling us to taste the sweetness of a mulberry, witness the magical glow of fireflies. The enzymes inhabiting our microscopic cellular world extract energy from food, driving the movement of our muscles. The proteins of our immune system keep a constant watch, protecting us from foreign invaders. And in the end, proteins may be our own demise, finishing the story of our lives with death. I want to... Thank you so much for having us. This is our shameless plug for our book. Please order it if you'd like. And also listen to our podcast, Rustbelt Science. This is, we sit down with scientists. We're like little kids learning about astronomy and physics and sharks. The one about sharks just came out today. Super cool. Michelle Jewell, who shows up on the Discovery Channel talking about sharks. She's a shark scientist, super amazing. Talks about her journey. Our aim is to really humanize scientists, and we're basically like little kids learning from them. Also, we have a few art pieces that Maggie and I worked on that we showcased in a couple of different places, and we wanted to share them with you. Feel free to walk around, ask us some questions. It's, the floor is yours, and we're happy to answer questions too, right? Are we allowed questions?
Yes.
Okay.
Please.
All
Yeah,
right.
we have time
All right.
for
Come on.
questions.
Yeah. Okay. Steven.
Hey, first of all, thanks, great, super fun. I can't wait to look at the art more closely. So, I guess I've got some sympathy for the scientists who don't communicate to the public more generally. And let me put that in a question. A lot of science is talking to other scientists. And it's hard to expect someone who's trained to speak to other scientists in the language of science to also speak to me, the non-scientist. So I think some people like Neil deGrasse Tyson or the old days, Stephen Jay Gould, who were really skilled, and maybe two of you, at translation. But should we expect all scientists to be able to do that, or some, or how do you divide up the labor? Because most of the time scientists are going to be speaking to each other about what's going on in the lab.
Right.
And so I'm sympathetic to their inability to come and talk to us about it. I don't take this wrong. I remember Jerry giving a talk the other day, a couple years ago, about his research, and about 2/3 the way through, I was like, oh, I'm just gone. But I'm enjoying the presentation. The slides are really pretty. But, so I don't know. I mean, I guess I have some sympathy for the scientists who know to just talk to other scientists to do the science. And how do we expect them, or whom do we expect to translate to the public?
Great question. I have a couple of things, and I'll see if Maggie also has some response to that. But the first thing is I completely agree with you. Not every scientist should be a science communicator. We don't all have that ability, and we don't. And also, I just want to say this, in an academic setting, that's not valued, and it's not academically monetized, if you will. Right? It's not rewarded at all. It's not anywhere part of our tenure. It's not anywhere part of our teaching if we're a teaching professor. It's not any part of our research if we're a research professor. So there's no incentivization for it. And again, not everybody's going to be a talented science communicator. That's fine. So we agree that not everybody should be out there talking to the public. But there are simple things that we can all do to relate to people on a personal level, because we are all human beings, right? So yes and no. But also on the other side, which you mentioned, scientists talk to other scientists, and how many times have we been to conferences that are within our own disciplines, and I'm listening to a talk, and after the first slide, I don't understand whatever the crap this person is talking about. We are poor communicators to each other too, right? This is a problem with communication, not just communication to the public. It just so happens that we do some communication to the public, but we also train scientists to be better communicators in general, because you can say it's a talent, and to some extent it is, but everybody can take art classes, even if you have like zero talent, and still be able to draw better than you started out with, right? So everybody can get better at it. Not everybody has to do it. Certainly not everybody gets a reward for doing it, but it's absolutely needed. And scientists are not great at communicating to other scientists either. We're terrible at communicating. Did you want to follow up on that?
Yeah, I was just gonna say I'm maybe slightly less sympathetic than you're offering to scientists. I taught a freshman biology lab today, and they don't know anything. And I remember when I didn't know anything, and then now I'm trained. I have my PhD, and so how do we forget that we didn't know that stuff at some point? I really can't fathom how quickly that leap goes from I don't know anything and somebody showed me how to do it to I am not going to dumb it down for you. I'm going to show off with all my big words. So I'm slightly less sympathetic, and I also strongly believe it is the responsibility on an ethical level for scientists to communicate their research. We're getting paid taxpayer money to do this work, and it doesn't mean we have to get up here and give great public talks and all this stuff, but it is our responsibility. Science is not done until it's communicated, and that goes beyond publishing in whatever impact factor journal, right? I think it's on us as scientists and academics more generally. So I'm slightly less sympathetic, and I do think that as science graduate students are becoming more diverse and coming from more backgrounds and more experiences, the drive to communicate their science to their own communities is much higher, right? Traditionally, there's been a lot of white men in science who come from families who are scientists. So now we're seeing this influx of students who are first generation coming from marginalized communities who hold a lot of anti-science beliefs, and so they feel that need a lot more deeply. So I'm hopeful that this new generation of scientists is coming in with that push of we have to do this because our communities need it, and they're seeking out that training and those opportunities a lot more. And now the push is that going to be rewarded by advisors, by professors and PIs, and then the academic system as a whole.
Yes.
If you're going to be a teacher, which many of us in this room are, you also have to be a good communicator. I also have been in academia long enough to know that teaching is not a form of communication that is often rewarded. And one of the things that made me return to IUSB after starting here in 1996 as a visitor was the fact that back in those days, IU also allowed us to value teaching. And it led to us having a campus where we have had a lot of really good teachers who have learned to communicate very complex ideas to students who are often themselves first-generation college students, like some of us are. And I think that part of what we're seeing here is a reflection of the fact that communication is not so valued because teaching has not been so valued. And that's not obviously just true in science, it's true in academia more generally. So not a question.
Word. Well, but I speak to the IUSB experience, and I think Maggie probably as well, because I'm a product of IUSB, and again, I say to my students right now, I wasn't born awesome. Somebody took the time, right? You're here, no, you're hiding back there, right? And a couple of you are here in the room, my professors, who took the time to actually explain these things to me in a way that a complete novice found it fascinating. I mean, I remember I was sitting in Anne's class many, many years ago, not that many years ago, not that many.
Years ago, yes.
So a couple of years ago. And I was learning about PCR, the polymerase chain reaction, and I was like, oh my God, this is a fascinating process. When I learned about it, it almost literally blew my mind. It made me think, like, who came up with this? Was this person on acid? Turns out he was. But that's the kind of fascination that was implanted in me, and I'm sure you agree. Yeah.
Word.
Yes.
Yeah.
An observation and a question. I really liked your slide about disinformation or misinformation traveling 6 times faster. This isn't actually my question. Do you have a citation for that?
I don't have it here, but I do have a citation, yes. I'll look it up and I'll send it to you. I know where you live.
That was a poor attempt. But something I like to do, I think finding the edges for where that misinformation meets the real world can be a really interesting teaching point. Like the NSF, the National Science Foundation, puts out periodically a survey of American readiness to understand science and technology products. Hopefully they'll continue to do so in the future. And they have like some really useful but also terrifying things like true false. The Earth goes around the sun, or actually no, I'm sorry. A or B, the Earth goes around the sun or the sun goes around the Earth.
Yeah.
Right? And 74% of Americans get that correct.
Yeah.
I mean, or lasers are concentrated sound. Which, and I go through this whole thing with my students when I'm teaching and I'm introducing them to evolutionary theory. It's like, why are you afraid of evolution? Let's think about why we think. We talk about what kind of sounds do different lasers make, like pew pew and
No.
right? So I think that's a great point. Anyway, I love your point about misinformation. My question is, I'd seen everything from Leeuwenhoek, all those images, except the sperm. Where did he get that? Because I'm thinking about preservation. And
Maggie? That's your slide. You're the microbiologist here.
I think it's self-explanatory. I don't know.
Self-exploratory.
So yeah.
Self-exploratory, yeah.
Sure. I don't know how well he documented his methods when he was doing this, but I think it was his own sperm.
I want to just touch on the point of misinformation. Misinformation and, in fact, disinformation, which is intentional misinformation, is a multi-million-dollar industry, Mark, because we have what I like to call, still, snake oil salesmen, right? Yeah. Who will sell you all kinds of stuff, by whatever claims they have, and it's completely unregulated. The health and wellness industry in this country and the world is worth billions of dollars, and the supplement industry is completely unregulated because it doesn't fall under Food and Drug Administration. So that there's a reason why that is a big business, especially here. Yes, Elizabeth.
You mentioned the importance of funding even research that seems kind of far out there.
Yeah.
I wonder if you could talk briefly about just the more general impact of not funding scientific research. And Josh mentioned
Yeah.
NSF. We also heard like FDA, et cetera. I mean, the current cuts in scientific research and
Yeah.
what that might mean for us, people in the country more generally.
Yeah, I think the answer, very simply, is it's going to screw us over. Not just as scientists, but as a country. Because the United States, as many of you probably know here, has been the pioneer in spending on science research, scientific research, since for the last 100 years, and even more so during the Cold War, because it's essentially Cold War, it's technology war. And based on that, based on funding what we call basic science research, meaning just what is this conch shell doing, things like that. And then from there you get all these therapies. And there's an estimate about, every dollar that you spend on research, how much you get back. It's something like, $2.50 or $1.75 or something like that in profit. So it is actually economically important for us to fund science research in general, even if it's not necessarily what we would call applied research. The other problem that's happening is the brain drain. So we spend all this money to train trainees like myself. I didn't pay a penny to go to graduate school. Maggie? No. In fact, we got a stipend to go and study our PhD because in the sciences you get funding from mostly the federal government, whether National Institute of Health or National Science Foundation. So thank you all for supporting our education. But that is an investment. It's an investment in all of us so that we can stay here. And now what's happening is after all of these trainees get trained here, then they get recruited by New Zealand or Australia or Denmark. I get ads on my feed to come do science in Denmark. We're not the US. Basically that's the message. So that's a huge burden too. So discovery aside, therapeutics aside, technology aside, which is also a security issue, right? National security issue, because if somebody else has a better technology that can hack us or whatever, that's beyond my understanding, right? That's a big problem. So it is a huge investment, but also that flight of scientists, at least what we think is happening. I don't have numbers on it, but that's a threat, is the brain drain. Maggie? No, good? Did I do good? Okay, all right, did great. Yes?
I've got a question. Well, first I wanted to say when you were talking about PCR, the mind blow,
Yes.
it reminds me, do you guys remember Gretchen used to say, don't you wish you invented that?
Yes, yes.
All the time. Don't you wish you came up with that?
Yes.
I was curious, thinking about, I love the connection that you made citing that book from Charles,
Charles Duhigg.
say the last name again?
Charles Duhigg.
Duhigg.
Yeah.
The connection between values and emotion, and it made me curious for the two of you, if you're thinking about our campus and our students, is there a science-related issue that is like your pet issue that you're like, I really wish there was a way to connect with students about this, to get their emotions and their values onto this issue? What would that be for each of you? I'm curious. Really, I want to know from all of my colleagues, but this is your talk, so please.
I just think I want them to value the educational process or the educational experience that they have beyond just a utility for a job. I think that's really my thing, is that this is going to benefit you as a human being. That science in a way is a humanistic endeavor because it helps you grow as a human being. It's helping you ask questions about the world and about yourself. And also, just, it's a good thing for you regardless of whether you end up getting a job or not. If you want a job, just go be a lawyer. But you want to make money, right? But the point here is that it's going to benefit you because hopefully those snake oil salesmen are now going to trick you because you can use your mind. So that's kind of the value that I try to. Did I do a good job, students here? Yes? Did I do a good job? Okay, thank you guys. Right. It's the same message, Dr. Rizk, right? Use your brain because it's good for you, right? Not for a job or anything, the job will come, but use your brain. Maggie, what do you think?
I think it's similar to what Shahir said, that science is not a list of things you have to memorize. It's something you get to experience. Like, I have looked under a microscope, I don't know how many times now, and every time I'm like, oh my gosh, this is crazy. How wild that this is the life that's happening around us, right? And sometimes I see students just dead in the eyes because they're so overwhelmed with, like, I have to know all this stuff. And it's not about knowledge, it's about just fostering this sense of imagination and curiosity. And this is not an obstacle, again, to you getting a job. This is an opportunity for you to just to connect with yourself, your neighbors, the ground under your feet, and you don't have to love everything. You can change your major and go be a psychologist and a therapist, and that's great. But don't forget that science is a part of that as well, and science is a part of you. And I don't care if you get a C in this class. Hopefully you go on. I got a C's in a lot of classes, Dr. Grenz. And so that's not the point of not because of her, because of me. But and that's not the point. That's never been the point of science. I mean, think of Leeuwenhoek. He was not a trained scientist, and he made significant scientific discoveries. And it's a way of life. We have a really great podcast episode where we interview a scientist at Notre Dame who talks about this humanistic approach to the scientist and the holistic scientist. And I think that is my goal as an educator for as long as I get to do it. Is we're not turning out science robots. We're creating human beings that can go out and experience the world and share that with whoever else that they interact with. Yeah.
I'm sorry, I'm still.
No, go ahead.
It sounded like both of you were speaking to science students. I'm curious, is there a thing, would you hope the same thing for non-science students, or art students, or humanities students? They have no perception, they're not memorizing in science classes. What would you want them to connect with about science?
Yeah, I am actually teaching a class for non-scientists right now, so I can speak to this. It's a similar thing, that science is a part of your life even if you don't realize it, and it's not this scary thing that you have to be super smart to know and understand. Right, I had a lot of my students walk into the first day of this class for the Master's in Liberal Studies program. Like, I'm not good at science. I've never taken a science class. I'm terrified of science. And because it is a science requirement, they are making some graphs. But now they can do it. Now they can look up a paper and they can understand things. And it empowers them to go out and seek out information and say, oh, I can understand this information, right? And that scientist is not this thing that's separate from what I do as whatever job I have. I have a librarian, I have a computer scientist, I have a mathematician, I have administrative people, right? Science is impacting your daily life. So one of the cool things that I've had my scientists do is there's this thing called a Winogradsky column, where you basically take a bunch of mud and water from the river or a lake and you put it in a bottle, and you put some paper in there and maybe some eggs, and that's basically food. And all the bacteria that are in the soil start to grow in these different levels with these different colors, and you have this beautiful column of blues, reds, oranges, greens. So I had all my students make that and take it home and put it in their windowsill. And that has been the #1 topic of conversation in their lives with the people around them. What is this column of dirt that kind of smells bad, right? So, they don't know all of the bacterial metabolism that's happening at all those levels, but it's sparking curiosity around them and empowering people to stay curious and to ask questions. And that scientists are really pretty much the same as everybody else. This is just what we do for our job, which we're very grateful to do. But it's the same, we're the same people. We have the same, right? Soccer, going out to eat and drinks. And so that's my message to my non-scientist students is you're a scientist as well, and you can engage in this and stay curious.
Speaking of soccer, Clyde, superstar.
I had another question, but I'll ask this first because it seems like it's where we kind of ended. I find this very difficult with my classes when I teach to other students that are saying are not economics majors. How do you approach it to show them that actually where it's actually valuable, but also to teach them how they will use them and more practical, right? Because a lot of the time it's very theoretical what we teach.
Yeah.
And if they do not see the actual use of it in their daily lives, it's kind of hard to convince them that they should care. It's just, it's a class I can take.
Yeah.
And I'll ask you the second one.
So a couple of things. one thing that I do, and I don't know if this works or not, because again, if there was like one magic way to do it, we wouldn't be here, we'd be talking about it. There would be no misinformation, all the students would get A's, and we would just be, we'd all get tenure immediately, and that's it. But obviously the answer is difficult. But one of the things that I do is, instead of starting with, what a carbon is or what a hydrogen is, things that seem to be completely irrelevant, start from something that they know about, maybe something that's in the news. Right? So one of the things that I do in my classes is have these discussion sections where we read something that's in the news, maybe something on like gene editing embryos or something that's out there in the news media, or something about AI. Everybody's talking about AI. Well, then we talk about how does AI actually apply to protein science, but really we have honest conversations about AI in general. And I ask questions like, how many of you are just terrified of AI? Right? We start there, right? We just start there. But yeah, exactly. And, some people raise their hands and we talk about the good things and the bad things and so on. And then hopefully that drags them or brings them into it. The other thing is, sometimes some of the things that we teach them, they will never actually use them. Never, ever, right? We've all learned long division, right? Long division, yeah, you remember that? How many of you have used long division since you actually learned it in the physicist, of course, right? How about long division, right? The vast majority, right? Because we have calculated, the vast majority of us don't. But what does long division actually teach us? And I think that's something that we can be honest about with our students. That yes, you may never need to calculate this equation ever again for these molecules. But here's what it's teaching you. It's teaching you how to ask a question, how to follow through with a problem, critical thinking, how to ask for help. All of these things are very important. So those are things that I'm just very clear about and saying, you may never use this. You might if you get my job after I die. Right? But also, you may never use it, but what you will use from it, this is just an example of how to use your mind. So again, those are a couple of things that I do. I'm sure there are other ways to get our students to be more engaged. Yeah.
The second one has to do with creativity. I watched these videos about this guy, I don't know if you ever heard, Sir Ken Robinson. He talks a lot about creativity and how early in school,
Yeah.
we focus so much on the side of the brain that doesn't, it's not part of creativity
Yeah.
in schools. And so by the time we see students, obviously that's a problem.
Yeah.
How do we
How do we bring that back?
make that better?
I have just one quick thing to say, and this is something that I say to a lot of people. I think that in the sciences we miss out a lot on creative people because they're told early on that science is about memorization and solving equations, and yes, there is that element to it, but honestly, I don't memorize anything because I can look it up. The point here is how to process information, but really science is about creativity. People who have an artistic background are generally going to be better at sciences, and vice versa. But we miss that. We miss that part because early on we say, do the long division again, right? If you don't do it, you're never going to be a good scientist, right? Turns out I was really bad at long division, but here I am, an example of failure to success. So we have to do better. Right? As a community, we have to do better. I don't know how to do it any better in my realm, but, convincing people that science, especially, because I'm just talking about my field here, science is really a creative endeavor. Maggie, do you want to answer that question about creativity? How we kill creativity early on?
Well, we just do. I mean, there's no room for making a mistake that's based in a creative thinking process, right? I have two thoughts, so I don't want to forget the other one. But for example, my son, he's very good at math. He's almost 13. He can solve a math problem but not in the way that he's taught how to do it. And then he gets frustrated because he's not doing every step that he was taught, but he gets the right answer because his brain just works a little differently, and it's really, really frustrating. He gets so discouraged, and then he doesn't try. And he's 13, so imagine if you are in college taking all these classes and you just don't get it, but it makes sense this way, but you lose the points and you don't understand why. So I think we need to be way more open with there's more than one way to solve a problem, and letting students explore that in some way. I haven't been teaching that long, so I don't have a ton of advice, but just from parenting and seeing that struggle in my own kid and experiencing it myself as well, like it makes sense to me this way, so why do I have to do it this other way? And the other thing that I have been exploring doing, mostly with my non-science students in the class I'm teaching, is yes, I have to do some type of assessment of did they learn the material, but the majority of my assignments for this course have been make an art project about it. Write a poem about this scientific topic that we explored in class today. Right, I want to see that you can explain something scientific that you learned. I want to see you be able to explain the scientific inspiration behind this sculpture that you're making. But my assessment of did they learn something is a little different and allowed them to express what they learned in a really different format. And that works well for a class that isn't a requirement for a biochemistry degree. But even in these spaces where the assessments and the outcomes have to be a little bit more structured and rigid because there's just a standard that you have to learn, allowing students I had a student today just doodling things in lab, and she was distracted about what she was supposed to be doing because she was creating these really cool pictures with the phylogenetic tree she was making. I was like, yeah, keep doing that. Please do your assignment as well. But this is great, right? You should be making art when you're learning science. So allowing space for that, to them to express their creativity and letting them have assessments and assignments where they can do that and figure out how they're learning to incorporate that creativity into something like science. I don't know if it's going to work. I'm just trying it out, but the students seem more engaged with me when I let them explore some of these ideas non-traditionally.
Yes.
I'm currently an undergrad at IUSB.
Awesome.
I think I have you next semester, Dr. Fink.
Oh.
Nice to meet you.
Hi, nice to meet you.
So how can I, as someone who obviously has like a very shallow well of knowledge about science, like communicate it better, especially when I have like a question about something, when I'm trying to understand something, I often feel like I'm like, does that make sense? Like I don't know how to kind of pull things together that I'm not an expert on, that I don't know for a fact, and then formulate that in a question to make you guys help me understand it better. Does that make sense?
Yeah, it does make sense. It can be challenging when a student asks a question and I don't know what their question is. I don't know what they're actually confused about because they don't have the words to explain. So first of all, I told the student last week, I am thrilled if you ask me a question. That's a win in my book. Any question is like, yes, now we can start from somewhere, right? If I don't know that you even have a question, then what are we doing here? So I think the other thing to remember is I tell students, you actually know more than you think. If you stopped for a second and actually imagine what you were learning, you're like, oh, I actually do understand the idea that there is a vapor pressure for water. I've seen these things in real life, right? These are not imaginary things. So you do have this kind of intuitive knowledge about the physical world around you. And so drawing from those experiences, even if it's not the technical right word, I think that actually hearing somebody ask a question using language that isn't jargon can actually expand our understanding of where a student is coming from, of how they're interpreting that information. It's actually very helpful. So keep asking questions. And it's a conversation between your professor and you of figuring out where that gap in knowledge is. And hopefully a good professor is like, yeah, let's have that conversation. And you shouldn't be intimidated by the fact that you don't know the technical right word. You're there to get an education, correct? And part of that is asking questions. And that's when you if you go to graduate school, all you do is ask questions. And you don't even know what questions you're supposed to ask there either. They're like, answer a question and also come up with a question, right? So that's just, you're starting off strong for grad school. So I think every professor who would be like, please ask the question and don't worry about it being right. And we'll figure out what you don't actually know, and then we'll teach it to you. I don't know what you think.
No, this is perfect. I can't add anything else. Yeah, Clyde, and then one more, yes.
One last one.
Yeah.
Where do we draw the line with misinformation? Because as scientists, at any point in time, we are most likely, very likely, or at least likely, doing misinformation.
Yeah.
It's the best we know at the moment.
Yeah.
Tomorrow may be
Yeah.
different, right?
Yeah.
So that's very difficult when we talk about misinformation, right? We can say this is misinformation today,
Yeah.
but maybe what we are telling people today and believe that it's the correct information may be misinformation.
Yeah, that's a great point. So I heard a talk by a guy named Holden Thorpe. He's the editor-in-chief of the journal Science, which is one of the biggest journals in science. Right? So, and he was under a lot of, he was just getting these threatening emails, and one of the people said, well, how much of what you're publishing in your journal is wrong? And he said, all of it. All of it is wrong. It's the best of our knowledge, but the fact that scientific progress keeps going means that we're always going to be a little bit better and a little bit better and a little bit better. So yes, it's wrong, but it's the best wrong that we have right now. Now that's different from misinformation. Sometimes misinformation can be a misunderstanding, right? I can explain how the immune system works to somebody, and then they can go away, thinking something else, right? Because I used the wrong word. So that's just a misinformation, as a misunderstanding, a misinterpretation of what the science is actually saying, right? So there is what the science is saying, which is not a complete picture because we'll never get there. But then there's either a misinterpretation, misunderstanding, or a miscommunication, kind of like the telephone, right? There's also the media. The media has a very big role in this because, when somebody publishes a paper that says, we found this molecule that might help with this kind of progression of this disease that's similar to cancer, but not, we only show this in cells and it's very early on. And what do the media, they share with the media? What's the headline? We cured cancer, right? And obviously that's not the case. So we have to also be responsible in journalism, and that's not something that's necessarily happening. And again, we're all susceptible to misinformation. All of us are susceptible to misinformation. But not just that, but also misinterpretation of the data that's right in front of our eyes, regardless of our, what they call numeracy score. So there is actually a study that came out about, I don't want to go into details, but basically the way you interpret the data, even if you're really good at science, you're really good at math and interpreting data, the way they interpret data on something as controversial like gun control, for example, you're going to ignore the numbers that you're looking at. You're going to go with whatever affiliation you have, whether you're a liberal or a conservative. That's just been there's been documented cases on that. So we're all susceptible to misinterpreting. So there's so many layers to it. Yes, there's the science that gets published. There's the stuff that people put out online. There's the misunderstanding. And then there's also our own biases, like where do we belong, kind of that last conversation. But then there's also the disinformation, which is intentional misinformation. That's just malicious, right? That's, again, that billion-dollar industry, right? We had one question over here, yes?
Wasn't a question, but based on the conversation, it would appear that a lot of you are working at the college level, and I would just like to encourage you that if you want, because with her question, as an undergrad trying to figure out, I teach high school, and so that's a thing that at the high school level we're trying to teach kids, right? But those things of getting the kids interested in science, that happens at the elementary, that happens at the middle school, that happens. So those of you that work at the colleges, please come invest in your community.
Please invite us.
Please come invest
Yes.
in the library programs
Yes.
and in the school programs. And also understand that as teachers we're exhausted, so we're going to ignore you.
I know. We're all overworked, and I would love to go into schools, but I don't know how to organize something like this because I don't have the administrative ability to actually do that. I don't know if I need a background check to go into a school. These are things that are real problems. Yeah.
Build connections with, so at least in this area,
Yeah.
build connections with individual teachers because it's going to be individual teachers that drive that.
Let's talk then. Yeah.
And I teach English, so I cannot.
Awesome.
Uh,
I'll come talk in your class about whatever. I mean,
But I think that would be a thing if you are working in the colleges,
Yeah.
if you can come invest in the community, or even I know the Science Alive program at the library is a great way to invest in the community and get kids at a younger age so that they don't think that science is scary.
absolutely.
And
Absolutely.
That I think would do a lot.
Thank you. Thank you for that. Let's connect for sure. Other questions? Sid?
Phenomenal job.
Well, thank you. Thank you so much.